for our lecture this week, we're going to look at basically another variation of the title on second order time response. So the title of this particular week chapter is time response of second order system. So we're still in time response of second order system, but now it will be done using what we call damping ratio and natural frequency. So what happens briefly is that if we look into previous chapter that you have studied last week, that we have looked at together last week, we have studied the time response of second order systems, but we did it like in the first order time response, which was studying and analyzing the system using the position of the poles, right? So we see that by knowing the poles, it was very convenient because we can have an estimation on how does the time response will look like for first order and second order systems. But now, particularly for second order systems, there is another notion that can be included, which we call the damping ratio and natural frequency, right? So in the first part of this video lecture, we will briefly describe what is the definition, what are the definitions of damping ratio and natural frequency, and why is it related only to second order system and it was not utilized for first order systems. And then we will try to analyze the second order system using these parameters of damping ratio and natural frequency. So at the end of this chapter, what we are expecting the student to be able to do at the end of this chapter is basically to be able to determine the time response. So you should be able to determine the time response of a second order systems using damping ratio and natural frequency, which also includes basically when we say that determine the time response, it will also include the criteria of performance of second order time response. So let's start. So before we go into the definition of what is damping ratio and natural frequency, let's remind ourselves about second order time response. So in summary, to summarize, basically second order time response can be characterized into 4 types of response, right? So basically we have, if we have the poles position on the real axis and distinct, we have an overdamped time response. If the poles position, so remember, if you revise a bit the chapter that we had last week, it was done, it was basically done in relation to the position of the poles. So if the poles position are basically 2 points distinct on the sigma or real axis, we will have an overdamped time response. But if we have the points both basically on the real axis, but now they are not distinct, they are at the same position, we will have what we call critically damped, right? And then the next one, if we have we start to have the poles position start to have a component of j omega, like in this green position, that would mean that we will have an underdamped time response. And finally, if both the position of the poles are situated only on j omega axis, like in this blue position, we would have an undamped time response, right? So this first description of the type, so we will call it as type or characteristic of second order time response, it was done in relation to the position of the poles, right? It was done in relation to the position of the poles. So this is again the repetition of what we've said just now. So overdamped for this position of poles. Underdamped is when you have the complex component as well with the real component. Undamped is only when you have the 2 poles are on the complex component, and the critically damped is when both the poles are on real component but they are both on the same have the same value, right? So this the relation between the poles and the type of the time response. But now, instead of so far we base the characterization of the time response based on the position of the poles, right? So what we did was so this is a little revision. How did we do that? Basically, from if we don't know what the type of time response it is, from the transfer function, what we do is we calculate the poles of the system. So the poles of the system is calculated or computed using the denominator of the transfer function. And how do we calculate it? So you can just plug in the formula of a quadratic equation or second order system equation to find out the roots or the poles, and then you'll end up with a certain position of poles, right? So this is an example. This is an example for an underdamped system. And then so once you have that, we have basically, if you remember last week, we have a characteristic general expression or general equation for the time response, and then we just plug in the value of our poles into the general equation of our time response, and we will be able to trace the time response. So that's what we did yesterday. But now we're going to learn another two quantities, not just the poles, another two quantities or parameters related to second order time response that will help us in describing a second order time response and basically analyzing the system, the second order system, with more ease, right? So the two parameters that we will help us in analyzing second order system is what we call natural frequency and damping ratio. So natural frequency is noted by omega n, and damping ratio is noted by the Greek letter zeta, right? Omega n and zeta. So natural frequency, the name is frequency, but it is noted with omega. It is basically a frequency in the unit, not hertz, but it is in unit of radian per second. So radian per second is also a frequency, but it's not in hertz, which is per second. Now it is in radian per second. And damping ratio, zeta, is a number with basically a unitless number. It's a number with no units. So let's see what are the definitions of this natural frequency and damping ratio. So the first one, natural frequency, omega n. Natural frequency of a second order system is the frequency of oscillation of the system without damping. So it is the frequency of oscillation of the system without damping. So what does this mean? So let's take a look at an example of time response. Let's draw a bit the time response of a second order system. So basically, if you remember, let's take an example for let's take an example of an underdamped system. Basically, for these two characteristics of natural frequency and damping ratio, it is very obvious to us to identify them when we look at an underdamped system. So what is an underdamped system? An underdamped system is basically a system that will have a few oscillation first before it goes to a certain steady state values, right? And we've said that in our S-plane, there are two components of sigma and j omega. And what does sigma represent? Well, sigma represents what we call the damping, not damping. It's what we call the decay. So, and j omega represents the undulation or oscillation. So the decay, what is the decay? The decay is the rate at which the response goes towards a steady state value, right? It decays towards a steady state value. And undulation, what does undulation means? So omega is basically not the rate, basically is a representation of the frequency of the undulation. So the definition of natural frequency is basically the frequency of oscillation of the system without damping. So what does it mean without damping? First, we have to eliminate the damping. Without damping means when we don't have any decay. So when the component of sigma is 0, therefore we will see that there is an ondulation. So this ondulation that has a certain frequency, that is the natural frequency, right? That is the natural frequency. So the frequency at which the time response oscillates, if there were no decay, that is what we call natural frequency. So let's have a look at an example to understand and identify the natural frequency of a system. Let's say we have now a second order system of, let me change into a pointer. So let's imagine um, we have a transfer function of second order system. So it's written as b over s squared plus as plus b. So how do we identify natural frequency? Natural frequency of a second order system is the frequency of oscillation without of the system without damping. What does it mean without damping? Without damping means basically means that we eliminate the decay. How do we eliminate the decay? We eliminate the decay by basically eliminating the second term of as here, this term. Because this term as in this quadratic equation, this term as is basically the term that is the term that introduced uh, the decay component. So if we eliminate as, what we'll have at the end now, the transfer function will become only b over s squared plus b, right? So if you find the poles of this new system without as, these poles will only have, so s squared plus b. If you find the poles or the roots, it will be s equals to plus minus j square root of b, right? Because s squared will be equals to minus b. That means, so s squared equals to minus b. It means that s equals to plus minus j square root of b. J square root of b. So j square root of b, if you plot it on a, if we plot it on basically on, if we plot it on S plane, so let's plot these new poles on S plane. So sigma and j omega, S equals to plus minus j square root j square root b. We will have square root b over here, and we have minus square root b here. So these are the poles of this new system without as, right? Without as. So if we look in at this system, what kind of system, what type of system, what type of second order system is this? This is basically an undamped system. It is an undamped system. How does an undamped system look like? It is a system that keep on oscillating without decay. So without decay. So without decay means we have no damping. So that's why if we want to find natural frequency, we will eliminate the decay by eliminating the term as. So if you have a transfer function and you eliminate the term as, and then you calculate the poles of the new transfer function without as, that poles will give you, for example here, it will give you that square root of b. Well, that square root of b is basically the natural frequency, right? That square root of b is your natural frequency. So omega n, the natural frequency, is the square root of b. Okay, this is the square root of b of your transfer function here. So b is this term, and also we can write, so for the sake of convenience, we can also write that b is omega n square. So if you write your transfer function as b over s squared plus as plus b, b is omega n square. If you want to find the natural frequency, it is square root of b. So that's how we find, that is the definition of natural frequency, and that's how we find the value of that natural frequency of a second order system. Okay. So now we go to the second term or the second parameters, which is the damping ratio. So the damping ratio is annotated by the letter represented by the Greek letter zeta. And what is damping ratio? Damping ratio is basically it's a ratio of the exponential decay frequency divided by natural frequency. So it's the exponential decay. Exponential decay is this part divided by the natural frequency, right? It represents the ratio between the decay and the natural frequency. If we have a high damping ratio, what does it mean? So try to analyze this. If we have a high damping ratio, that means the decay is very, very important compared to the natural frequency. So you have, for a certain natural frequency, the decay is very, very quick. What does it mean to have a very quick decay? If you have a very quick decay, so instead of having, for example, this blue line here, instead of having the thing that we have here in blue line, the decay will be much, much quicker and much, much harder. So it will decay a lot quicker. So your time response will look like this. It have less overshoot compared to the one here. If you have less decay or less damping ratio, if damping ratio is lower, then your exponential decay will be also slower, which also means that your time response will have a higher overshoot. So that's what damping ratio means. Higher damping ratio, it means a more severe or a more severe decay, a quicker response toward the steady state. If you have less damping ratio, means you have more oscillations, more overshoots, and you'll take more times to go into the steady state. So now let's see how do we calculate. So after having looked into the definition of the damping ratio, how do we calculate the value of this damping ratio? So again, if we have the second order time response written in this form, this general form of b over s squared plus as plus b, if you want to identify the damping ratio, so the damping ratio is the decay, so the rate of decay. So just now we've seen that the rate of decay is the component that is in the middle here, as. So it's a divided by the frequency. So the frequency is in damping ratio, it is quantified by 2 omega n, right? So the damping ratio is a of our transfer function here divided by 2 omega n, So omega n, again, if I ask you what is omega n, so omega n is square root of b. So those are the definitions of natural frequency and damping ratio, and we've also shown you how to calculate and identify both natural frequency and damping ratio in a generic transfer function of a system written in this general form. So basically, if we want to identify that particular parameters of damping ratio and natural frequency, it is important basically to write your transfer function in the general form of b over s squared plus as plus b. That means if you have any transfer function, try to rewrite them in this form of b over s squared plus as plus b. Okay, now in relation to the parameters of damping ratio and natural frequency, so let's identify here. We can also write it basically not in terms of b and a. We can also change b and a into parameters that is written now in terms of as a function of natural frequency and damping ratio. So natural frequency, what is natural frequency? Natural frequency is basically omega n, and omega n is equals to square root of b, if you remember. And damping ratio written as zeta. What is zeta? Zeta is basically a over 2 omega n. So from here, what we can do is We can also basically, another interesting thing is that to write your transfer function, right, the same transfer function, but now not written with the parameter a and b, but replace a and b with omega n and zeta. If you write, so basically if you replace b with so what is b equals to? B equals to omega n square, right? And a, what is a equals to? A is basically a is zeta. So if we look at here, what is the definition of a here? A is basically zeta multiplied by 2 omega n. If we replace this in the transfer function, you'll get a new writing of transfer function. So the transfer function can be also written in the parameters of in the parameters of natural frequency and damping ratio. If you write it in natural frequency and damping ratio, the general form of transfer function of second order will be omega n square over s square plus 2 zeta omega n s plus omega n square. So this is a very interesting kind of writing, because just by looking at this transfer function, which is now written in omega n and zeta, so natural frequency and damping ratio, you can directly guess or pre-evaluate the time response that you will have, because you can see directly what is the damping ratio and what is natural frequency. So basically, if you look at this transfer function, you can identify, oh, okay, now I have this kind of natural frequency, omega n square. So if omega n is very high, it means it has a lot of oscillation. If it has less omega n, then it means the oscillation is very slow. If we have, okay, I see that zeta is a very high. If zeta is very high, it means the decay is very quick, right? It has less overshoot. If zeta is very low, it means it will the decay is very slow, so it will goes into steady state response. It will take a lot of time to go into steady state response, right? So this is very important and very interesting to write the transfer function as a function of omega n and zeta. So let's try it out. So imagine now, so let's try to write our transfer function in a form with omega n and zeta, which are natural frequency and damping ratio. So imagine here we have that our new transfer function of 36 over s squared plus 4.2s plus 36. So how do you find the damping ratio and natural frequency? How do you find the damping ratio and natural frequency? So you can pause this video, for example, for a few seconds and try it out. Go back and look at the slide. How do you calculate the transfer function and how do you calculate, how do you calculate the natural frequency and damping ratio? So now I think you can figure it out. So we know that omega n square is basically is b, right? Omega n square is b, because this transfer function, generic form of transfer function, can be written as b over s square plus as plus b. We can see here that b is 36, right? And a is 4.2. So natural frequency omega n square is equal to b. So we know that omega n is 36. Therefore, omega n, or natural frequency, equals to 6, right? So that's easy. So now what about for the damping ratio zeta? So damping ratio, we know that damping ratio is 2 zeta omega n, which is a, right? If you look into the previous slide, so a is 4.2, so 2 zeta omega n is 4.2. So we can therefore deduct that zeta equals to 0.35. So for this particular transfer function or this particular system, we say that we have a natural frequency of 6 radian per second, and we have a damping ratio of 0.35. Damping ratio of 0.35. So now that we have defined the two terms of parameters of second order time response, which are natural frequency omega n and the damping ratio zeta. So let's see how do these two parameters affect the type of response of second order system, right? So second order system in our previous studies, the type of the time response was defined by the position of the poles, but now as the transfer function can be written um, in using these two parameters omega n and zeta, natural frequency and damping ratio, we can therefore try to identify the type of response in relation to these parameters of natural frequency and damping ratio. So now in previous slide we have defined the general form of our transfer function not with a and b but with omega n and zeta n. So this is the general form of the transfer function. So I think it's better for you to remember, or if you don't remember, basically at least remember the definition of omega n and zeta n in order to be able to come out with this equation. So gs in general form as a function of omega n and zeta n is equals to omega n square over s square plus 2 zeta omega n s plus omega n square, right? So if you want to identify the type of response in relation to omega n and zeta, what do we do? So what do we do is like what we have done before. We find the poles, right? So now we find the poles and then plot the s-plane and then plot the time response. Okay, but now instead of having your poles position as a function of a and b, your poles position will be in function of omega n and zeta. So the same thing, find the poles means finding the roots of your denominator of this polynomial, second order equation. So if you do that, then you will find that your poles are in this form, right? So your poles will be minus zeta omega n plus minus omega n square root zeta square minus 1, right? So there's one poles that has basically that will have plus omega n square root of zeta square minus 1, and another one minus omega n square root zeta square minus 1, right? So this is here at the bottom here is the general form of poles position of any transfer function of a second order system, right? And expressed in not a and b, not expressed as a function of poles. Now it is expressed in omega n, natural frequency, and zeta, which is the damping ratio, right? So if we look at different values of zeta, we will see that the types of the time response will change. Why? Because the zeta, so basically here we have two terms. The first terms on the left hand side, and after plus minus we have the second term with a square root. So this left term will always be a real number, right? Because zeta and omega n is basically, so what is omega n? Omega n is b square, it's a real number. And zeta, what is zeta? Zeta is basically a over 2 omega n, which is also a real number. So this will be a real number. So the thing that will change, that will be variable, is basically this term here, omega n multiplied by square root of zeta square minus 1. So what happened here? What happened here is basically we have a square root. So we know if the square root, the terms inside the square root is a real number, then it will means that the whole poles are real number and it will be situated on the sigma axis. But if zeta square minus 1 is smaller than 1, smaller than 0, which is negative, then our square root will becomes a complex number. So our poles will have a complex component. So just by looking at the expression of the poles in function of omega n and zeta, we know that we will have different types as a function. We will have different type of time response depending on the value of zeta. So let's have a look at it. So for the first one, let's imagine if we have the case where zeta equals to 0. So what does it mean to have zeta equals to 0? Zeta equals to 0 means we have a damping ratio of 0, right? Damping ratio of 0. If we have a damping ratio of 0, it means if you look into the definition of zeta, zeta is a over 2 omega n. It means a is 0, so no decay at all. So we can predict even before we do any calculation that the response will be an undamped response. It will be an undamped response, and we will have therefore the position of the poles strictly on the j omega axis. So let's have a look what happens if zeta equals 0. If zeta equals to 0, what will happen here is basically the term zeta square is also 0. So this term here is square root of minus 1, and we know that square root of minus 1 is basically the definition of j. So our transfer function have becomes now, if I can write it out, that our poles position will now become minus zeta omega n plus minus, so this term will become j, so it's j omega n, right? J omega n. And we know that zeta equals to 0, so this term will also become 0. So we're left with the poles S1 and 2 equals to plus minus j omega n. So that's what have been plotted here, j omega n and minus j omega n. So it is an undamped response. So next time, if you have your poles, so basically it's written like this. If you have your zeta equals to 0, you don't have to do any calculation. By knowing the definition of zeta and omega n, we know that if you have a transfer function with zeta equals to 0, then you will have an undamped response. So that's the convenience of knowing the definition of zeta and omega n, and that's the convenience of writing your position of poles as a function of zeta and omega n, right? So that's the first case where we have zeta equals to 0. So let's look at the next case. So again, so we have deduced before that the position of the poles, the expression of the poles is like this, right? So the second case is when zeta, so second case is when zeta is between 0 and 1. So zeta is between 0 and 1. So let's imagine it could be 0 0.1, 0 0.2, or 0 0.3, or 0 0.5. So no matter what value it is, we are looking at values that are situated between 0 and 1. So what happens if it's between 0 and 1? We know that zeta is between 0 and 1. So zeta square will also be between 0 and 1, right? So 0 and 1 means it's smaller than 1. So if we do minus 1, then the value in the square root will becomes negative value, right? So it's a negative value because zeta square is smaller than 1. Smaller than 1 minus 1 becomes a negative value. If we do square root of negative value, what does it mean? It means that here we'll have, basically, we will have a j term, and then omega n multiplied by with the value that we have in here. Right? So let's see. So we will have that the poles that we have will be equals to minus zeta omega n, so this doesn't change, plus minus j omega n square root of, so zeta square minus 1, it can also be written as 1 minus zeta square, right? 1 minus zeta square with a j in front. Why do we write 1 minus zeta square? Because basically zeta square is smaller than 1. So imagine if it is 0.5. So if we do 0.5 square minus 1, this is also equals to, what is it equals to? It's also equals to 1 minus 0.5 square, but you put negative at the front. So this negative has become j, and this term basically is here, 1 minus zeta square. So now this is your new expression of poles position when we have the case of zeta between 0 and 1. So where are the poles? So now zeta is not 0, so we have this real component, and we also have this complex component. So the real components and complex components mean we'll have the position of the poles over here, right? So we'll have one poles at minus zeta omega n plus j omega n square root of 1 minus zeta square, and another pole is at minus zeta omega n minus j omega n square root 1 minus zeta square. So what is this type of time response? So you have two distinct points with complex components. That means you have a response of underdamped response, right? This is an underdamped response. So for zeta between 0 and 1, we will have an underdamped response. So let's look at the next case. We know that we have four cases, right? So the next case is when zeta equals to 1. So zeta equals to 1. So zeta equals to 1 means the damping ratio is 1. So what does it mean when we have damping ratio is 1? So let's have a look at it. If I change into my pointer, so we have 1 minus 1 means 0, so we have no terms in omega n. Plus minus omega n here, we have no terms whatsoever here. So our poles will be only equals to minus zeta omega n. So we don't have that plus minus value. So it eliminates the possibility of having two distinct points, because the two distinct points come from this plus another point. Plus is 1 point, minus is another point. Now that we have this term equals to 0, it means both poles, both positions are located at the same point, which is minus zeta omega n. So if you plot it on S-planes, it's basically both of them are real numbers and they are at the same point on the sigma axis. So what is this? This is basically, if you refer into our previous lecture, this is a case of critically damped. So if you have zeta equals to 1, that is the case of critically damped system. And here we have the last case. So the first case that we've seen is the case when zeta is smaller than 1. Then we have zeta between 0 and 1, and then zeta equals to 1. Now what happens if zeta is larger than 1? The final case. If zeta is larger than 1, then the terms maintain. So zeta square minus 1 is zeta square minus 1. It's written just like in this form as well. So what happened is basically, but in this case, zeta square minus 1, is it negative? It will not be negative. Why? Because zeta is larger than 1. So a number larger than 1 minus 1 means the term here is positive. So the terms inside the square root is positive. So it's plus minus a real term. This is not a complex term. So if it is not a complex term, it means the whole poles. So now these whole poles are real numbers. They are real numbers, but they have two positions. So there are two distinct positions in the real axis of sigma. So we know that if we have pole position in such condition, we have an overdamped system. So there you go, the four cases of undamped, underdamped, overdamped, and critically damped and overdamped cases look in point of view of the value of zeta. So if you were to summarize, so if you write a transfer function in relation to, so if you write the transfer function with the parameters zeta and omega n, it is sufficient to look at the value of zeta to guess basically the type of the transfer function that you have, the type of system that you have. So we've seen that if zeta is larger than 1, then it is an overdamped system. So zeta, what does zeta mean? Zeta is damping ratio. If damping ratio is large, so basically the nominal value is 1. If damping ratio is larger than 1, then we have an overdamped system, so no oscillation at all. If we have zeta equals to 1, we are in the ideal cases of critically damped. If you have zeta between 0 and 1, then you would have your system underdamped, right? You start to have some oscillation. And if you go lower and lower until zeta equals to 0, that means you have no damping at all. You have the damping ratio equals to 0. It has to become an undamped system. So an undamped system without any final steady state value, right? So where do we get zeta? Again, we get zeta in your equation written as a function of omega n and zeta. So zeta is basically the term in the middle here of your polynomial. the term in the middle is 2 zeta omega n s. So if you have any transfer function, you need to first and foremost try to write it in this form. So you have the same term here, omega n square, uh, in this two part, and here with no coefficient in front of s square, and you have 2 zeta omega n s in front of the second term that is multiplied by s, right? So that's where you get zeta. So once we know zeta, if you have the transfer function that's written in this form, you can identify zeta. If you can identify zeta, you don't need to find the solution to your system and do the inverse Laplace and partial fraction and so on, just to deduce what is the response. Just by looking at zeta, you can already guess whether the system is overdamped, critically damped, underdamped, or undamped, right? So now let's do several exercises to understand how do we do this? How do we define the type of system using damping ratio and natural frequency? So let's take an example of this transfer function. So we have Gs equals to 400 over s square plus 12s plus 400. So what do we do to deduce what type of what kind of time response of second order it is? So what we need to do is first and foremost to write them in form of the general transfer function, basically general transfer function written using omega n, the natural frequency, and the damping ratio zeta. So what is the general form of transfer function written with damping ratio and natural frequency? So it is basically, if you remember in previous slide, it is omega n square, so the natural frequency square, divided by s square plus 2, so zeta omega n s. So zeta is the the damping ratio multiplied by natural frequency s plus omega n square. So it needs to be written in this form so that we can identify zeta. If we can identify zeta, then we can identify the type of time response of that systems. So let's do this for this example. So we have 400 over s squared plus 2s plus 400. Is it now written in this form? Yes, it is written in this form, with this 400 being the omega n square and 12 being the 2 zeta omega n. So we can therefore deduce that omega n is the square root of 400, which is 220, I'm sorry, and zeta is basically, if you want to find zeta is basically 12 divided by 2 divided by omega n. So 12 divided by 2 divided by 20 equals to 0.3. So now we have, so how do we deduce the type of system is it? Second order system. We have zeta equals to 0.3. So we are in the case of zeta between 0 and 1. So what will you have in time response? So for zeta between 0 and 1, we will have an underdamped system, right? So you see how does it work, right? So you have a transfer function. When we have a transfer function, we try to identify zeta. So in order to identify zeta, we have to make sure that it is written in the general form. Once you identify zeta and omega n, so once it is written in that form, you can identify zeta, omega n, the natural frequency, therefore identify the damping ratio zeta, and then determine the type of time response. So there are other examples. So let's see here, 900 over s square plus 9s plus 900. So again, here is written in the correct form. We have 900, which is the omega n square. So omega n will be square root of 900. And we have 90 here. 90 is basically 2 zeta omega n. So we can deduce that omega n is 30 and zeta is 1.5. So we have a zeta that is larger than 1. So in which case we will have a time response of, so damping ratio larger than 1. It means it is overdamped. It is an overdamped system with no oscillation. And then the next example, we have 225 over s square plus 30s plus 225. So we have omega n square is 225, and we have our 2 zeta omega n is 30. So we will have omega n natural frequency of 15, and we have a damping ratio of 1. If we have a damping ratio of 1, it means that we will have a critically damped time response. And then finally, of course, this will represent the last case where we have omega n square equals to 625. And do we have zeta here? So zeta is basically 2 zeta omega n s. There is no term multiplied by s. So that term is 0, which means our zeta is 0. So if you look at it, so we have omega n, the natural frequency is 25 radian per second, but our zeta is 0. So we are now in the case of undamped system with no damping ratio at all. So that's how, from a transfer function, just by identifying what is the natural frequency and the damping ratio, you can directly determine the type of time response that you will have. So you see, for second order time response, it is much quicker to basically to guess the type of response just by looking at these two parameters without going into calculating the output CS and then doing the partial fraction, inverse Laplace, and so on and so forth. Just by looking at natural frequency and the damping ratio, we can determine the type of time response. So now that we have identified the type of time response using natural frequency and damping ratio, the last part that we would like to do analyze on the second order system is basically to identify its performance, right? To identify its performance, and in identifying its performance, we need to specify here in this particular subsection of the chapter, we will treat as one case only, which is the case of underdamped, right? Why do we treat the case of underdamped? Because basically what are the other cases? We have 4 cases, right? Can you tell me what are the cases? So the cases that we have is basically is depending on the value of zeta. So zeta, there are 4 cases. So for zeta equals to 0, it is an undamped system. For zeta between 0 and 1, it is an underdamped system. For zeta equals to 1, this is what we call critically damped system. And for zeta larger than 1, this is an overdamped system. So for undamped system, we're not going to be we are not interested in undamped system. Why? An undamped system is a system that has no final values. It is not the system that you want. When we control a system, we want it to respond and give us a certain finite answer, finite position, right? For example, so for this kind of system, there are no criteria of performance that would interest us at all, right? What about the other two systems of critically damped and overdamped? So why do we treat only the underdamped case? Well, basically for critically damped and overdamped, how does the time response look like? Can you tell me? So critically damped, it means it is critically damped so that there are no oscillation, and overdamped is basically it is so overdamped that you can see no oscillation at all. The similarity between both these things is that we don't see, so basically we don't see any oscillation in the time response. It looks like this. It looks like this. It is not like in an underdamped system. In underdamped system, you'll be able to see a sort of oscillation at the beginning here, right? But in critically damped and overdamped system, there are no oscillation at all can be observed. It is strictly without oscillation. So a system without oscillation, basically it resembles to a first order system, right? It resembles to first order system. So if we want to evaluate the criteria of performance of critically damped system and overdamped system, it can basically be done using the indicator for performance of first order system. What are those? So those are basically the time response, the time constant, just like in first order time response. So you can refer to that chapter again. So it's just like in first order, but in underdamped system, we have now a particular case where we can see an oscillation. Now it's different from first order system. That's why in this particular subsection, when we study the performance of second order system, we will only treat the case of an underdamped system, right? So that's the why of we only select this case to study the criteria of performance of second order system. So let's start on the criteria of performance. So we'll study only for underdamped system, which means zeta is between 0 and 1. So there are 4 performance parameters that we can evaluate in this system, in this type of system. So the 4 criteria of performance, 4 parameters of performance are: the first one is what we call rise time. Second one is peak time. So rise time, we'll see the definition of this. Peak time. The third one is percent of overshoot. And then the fourth one is settling time. So settling time and rise time, this might be similar to the first order system, right? We have seen this kind of criteria of performance in first order system, but this number 2 and number 3 parameters are specific for second order time response, underdamped second order, which is peak time and percent of overshoot. So let's look at their definition and how do we identify them on the time response. So the first one, rise time. So again, the rise time is just like in the first order. So rise time, the definition is basically the time that it takes for the system to go, the waveform or the response, to go from 0.1% of the response to 0.9% of the final response, final value. So if we have to draw the time response, let me see if I can have my pen. So a time response, it will look like this, right? So the time that it takes, so this is the final value, right? And then the time that it takes for 0.1 of the final value until 0.9 of that final value. So basically, for example, the time from here to here, this is what we call rise time, right? Rise time. Rise time is the time that it takes for the system to go from 0.1% of the final value to 0.9% of the final value. So the thing that's different with first order system is that there are no precise analytical equation or formula to find the time response. We don't have any precise analytical relationship or equation, if you wish, to calculate the time response. So how do we do this? In order to find the time response, we must use a graph. So basically, in a system, usually what happen in a system, what we need to do is we need to do a certain experiment, right? And we change the damping ratio of the system. So as a function of damping ratio, what happen is the product of omega n and tr will change, So this graph for a certain system, usually you will be given, So for a certain level of damping ratio, you will have a certain value of omega n tr. If you know the value of omega n, you can therefore know the value of your time response, tr. So for example here, for this particular system that is illustrated here, for a damping ratio going from 0.1 to 0.9, of course we only go from 0.1 to 0.9, right? For an underdamped system, the normalized rise time, the rise time will be in the column that's found here, right? So we will have a graph to identify the rise time, not an equation as in the first order time response. So the next criteria of performance is peak time. So what is peak time? So peak time is basically the time that is required for the system to reach the first maximum peak. So the system, the time response have an oscillation, and because of that oscillation, it will attain a certain peak, a certain maximum at the beginning. So this particular peak, the time that it takes for the system to reach this peak is what we call peak time, TP, peak time. And for peak time, there is an equation that you can use to find that peak time. So the equation is over here. So peak time can be calculated by pi divided by natural frequency multiplied by square root of 1 minus zeta square. So if you have eyes on it, basically omega n multiplied by square root of 1 minus zeta square, this is the second term of your poles, right? This is the second term of your poles. So Basically it's pi divided by your second terms of your poles. Right? So that's how you find your peak time, the time that it takes to reach the peak of the time response. So the next criteria of performance, the third one, is what we call percent overshoot. So this is very important for an underdamped system. So what is percent of overshoot? Percent of overshoot is the amount of waveform that overshoots the steady state. So it represents basically how much does, so in so let's put it like this. So in a very good responsive system, if we ask it to attain a certain value, C final, value final, what happens is that it will reach that value as quick as possible without any oscillation. So that is a perfect system. We ask it to go here and will go directly, quickly. But in an underdamped system, it won't be able to do that. It will have a certain ondulation. Therefore, there will be values of time response that is basically higher than the value that you wish to have at the steady state. So at the beginning, at the peak of your response, you will have what we call overshoot. So it overshoot the final value that you want to attain, this overshoot. So this percent overshoot represent how much overshoot do you have. So if your percent overshoot is very high, it means your peak is very high compared to your steady state. If your percent overshoot is very low, that means your peak is very low, or it is very close to the final value, right? And how do we calculate this percent of overshoot? We have this particular formula. The percent of overshoot is 100 exponential product in the middle. So this is the same product as you use in order to find the rise, not the rise time, to find the peak, what we call, to find the peak time, right? To find peak time. So it's basically 100 exponential peak time, right? So that's how we calculate the percent of overshoot. And finally, the criteria of performance in a second order system is settling time. So settling time is, in terms of definition, is the same as in the first order system. So it's basically the time required for the system to reach within 2% of the steady state value. So basically to reach 98% of the final value. So it's very close to the steady state, right? So it's over here the time it takes for the system to reach this value, which is 2% close to the steady state value. And we have also a formula to calculate it. So the formula is settling time is 4 over zeta omega n. 4 over zeta omega n. So zeta being the damping ratio and omega n is the natural frequency. So let's be a bit critical on this. What happens if we have a higher damping ratio, which is a lot more closer to 1? Of course, the damping ratio will always be equals, will always, for an underdamped system, it will be always in between 0 and 1. But what happens if we have a lower or a higher zeta? So imagine if zeta is closer to 0.1. If zeta is closer to 0.1, it means this value will be at the lowest value, lowest possible value. If this value is at the lowest possible value, it means Ts will be high. Ts will be high. So if your damping ratio is low, if your zeta is low, what happens is your Ts will be high. What does it mean Ts high? Ts high means Ts will move further to the right hand side. It means the system is less responsive. So you get the final value with a lot of delay. But what happens if you have zeta very high? If you have zeta very high, which tend toward, for example, 0.9, what you will have is you have a lower Ts. So your Ts will become lower. What does it mean? It means Ts tend to go toward the left hand side. So what does it mean is that the system will be more responsive. So if we have a low damping ratio, of course, a low damping ratio means you will not see an overshoot, but your time response will also be your time response, or your settling time will also be late. So it will be something that looks like this. Right? So this is for zeta tends toward, let's say, 0.1. But for a high damping ratio, I'm sorry. So this is for high damping ratio. Zeta tends towards 0.9. But for a low damping ratio means you have more oscillations, but it will reach the steady state much faster, therefore more responsive. So it is always a trade-in between overshoot in the second order time response. It's always overshoot versus uh, time response, time constant or settling time. If you want to have a very responsive or a small time constant, a small settling time, you'd have high overshoot. But if you want to have low overshoot, your time constant will be, or your settling time will be very, very high. So it's always, what it basically means in simple word is, if you want the system to be fast, then it will oscillate a lot. If you want it to not, if you want it to not oscillate at all, it will not oscillate, but the time it takes to reach steady state value will be much longer. So that's the trade-off of a second order system. It's always overshoot versus time constant or settling time. So it's the balance between both that a control engineer has to play with, have to balance, right? So now we have an example of a transfer function, right? GS is 361 over S squared plus 16S plus 61. Now what we can do is, first thing is to write it in as a function of omega n and zeta. Therefore, find omega n and zeta. And if you have found omega n and zeta from the previous slides, you know that you can find settling time, peak time, rise time, and percentage of OS, right? Of course, rise time will need a certain graph to find it. So for example, now from this, we know that, so 361 are basically omega n square, and 16 is basically 2 zeta omega n. So we deduce that omega n is square root of 361, which is 19, and zeta is 16 over 2 times the omega n, so it is 0.421. So knowing that, we can therefore calculate the settling time. Settling time is 4 over zeta omega n equals to 0.5 second. And then we can also calculate the peak time. Peak time is this formula, right? So peak time is pi over omega n square root 1 minus zeta square. And then we can also calculate the percentage of overshoot, which is 100 exponential of peak time. So it will be equals to 23.3%. So we have 23.3% of overshoot. It means that we will have, basically, if we have a time response like this, so this portion is basically 23% of the steady state value, right? So that's how you calculate that. And then how do you find the rise time? So in order to find the rise time, we look at the graph that we have provided, and then we know that the damping ratio, our damping ratio zeta, was calculated previously, which is equals to 0.421. If we go to 0.4, we will have basically a normalized rise time at around 1.4, 1.5, right? So it's around 1.4 and 1.5. Not the rise time, it's rise time multiplied by omega n. So rise time multiplied by omega n is around 1.5, and then to find the rise time, you just divide by omega n. So you find a rise time of 0.079 second, right? So basically that's all about second order time response. We have in this particular video lecture look at the definition of damping ratio and natural frequency, and we have used them in order to rewrite our transfer function. We also have basically write the expression of the poles using the parameters of natural frequency omega n and damping ratio zeta. and then we have also identified the different cases of value of zeta and the corresponding types of time response. And at the end, we have basically studied and analyzed the criteria of performance of a second order time response in underdamped case, right? We have looked basically what is rise time, how do we calculate them, what is settling time and the way to calculate them, and as well for percentage of overshoot and another parameters as well. So that's all for this week video lecture. So please do the quiz that I will attach with this video lecture. You can refer to the slides to accompany the explanation in this video lecture, and I'll see you next week with the next subchapter. Thank you and see you next week.